This session is so that we can have a look at analysis of DTPA extraction of soil data using R this time instead of Microsoft Excel. So I'm actually going to use the package R Commander, which is a point and click interface to R if you haven't used that before. So we'll have a start with that, and I'm just going to start up R. Okay, so we get this window, and my straightforward way to start up a package is to use library or require, and then if you know the name of the package you can just type it in and hit enter. Okay, so the other thing that we need to do, I guess, is to get some data in there. The data will be supplied to you as an Excel file or a comma-separated values file. I'm just going to have a look. So basically you'll get a data file, looks something like one of these, all right? And in order to get it into R Commander, I favour saving as a simple comma-separated values file, but R Commander can import Excel. So we've got the data there. I will get rid of that, and we'll use the R Commander import data option. So I'll go to data, import data from a text file, and I'm just going to call the data, for want of a better word, E5, short for ENVT5510. It's a comma-separated value file. I'm going to look for it on my computer, so it's local file system. Decimal point character is period, as you'd expect. Not all of you maybe have grown up with that. Okay, so I hit OK, and I can go and look for a file. I know roughly where it is, so it's in this folder here, and I'll select the file that I want, and it will give you a message down the bottom. The data set E5 is 26 rows and 68 columns. I probably favour looking at a summary of the data too, so statistics summaries active data set. It says there's 68 variables, well, whatever. I wouldn't do it if I didn't want to have a look at the contents just to make sure they've read in correctly. So what I'm looking for here is that any numerical variables all have maximum, minimum values, and sometimes NA values. So in this case, concentration of cobalt by DTPA has got 12 missing values, therefore so is the log transformed version of that, and so on. Now there's no factors yet in the data set, but we're going to make one later on. So that seems to have worked quite well, and the types of things we went through in lectures to just investigate our data. So one of the first things we can do to explore our data is to generate a correlation matrix, and using R Commander it's very, very straightforward. It's under statistics, summaries, correlation matrix, and I'm going to pick this as the variable of interest, the fraction of zinc extracted by DTPA as a proportion of total, as we discussed in lectures, and as I'm just going to use a restricted range of predictors, so our table fits on the screen mainly, and it's easier to explain what we're doing. So let's try that. We'll just we know that total zinc is probably a good predictor, and we'll go up to the top. Total aluminium, and I'm using log transform values because I suspect that they'll be better distributed. And total calcium. So total aluminium can be a proxy for clays. Total calcium represents carbonate minerals, probably in our system. Almost always a good idea to put in total iron, and we'll pop in, let me think, let's put in organic carbon and pH and probably total silicon, although these are Aqua Digest total, so silicon's a bit wobbly, but there we go. And I select pairwise complete observations and check pairwise p-values and click OK, and I ended up with a correlation table. We'll scroll up and have a look at just the basic correlation table. Alright, and this is for exploratory data analysis, may be enough. If you get fussy, you can use the p-values if you like, but remember we're going to focus on what's happening in this case to one of the elements extractable by DTPA. In this case, the proportion of zinc extractable by DTPA as a proportion of total zinc. Alright, so what's it got reasonably high correlations with? And you know, it's a little bit subjective as to what's a reasonably high correlation, but there's one there. Not surprisingly, iron, and the more iron we have in the soil, the less, because it's a negative correlation, the less extractable zinc becomes by DTPA. Not surprising, because either it's strongly absorbed by iron oxides, or the association with iron is being included in an iron oxide precipitate or something like that. Okay, so that seems to make sense. We've also got reasonably high correlations with total silicon, okay, which is interesting, and I'm not sure what that means, partly because of the shortcomings of the analysis and partly because that would be unexpected, although it may relate to clays. And the final highish number that we see seems to be total zinc. So the more zinc we have, effectively the less extractable zinc becomes, which is in some ways counterintuitive. It depends on what we assume is the mechanism which is holding zinc in a non-extractable or non-bioavailable form. If it's adsorption, then this would be completely unexpected, because we'd expect the more zinc in the soil, the more we'd tend to fill up the strong adsorption sites, and there'd be more left over on weaker adsorption sites. And so we'd expect a positive correlation, but the negative correlation suggests that iron precipitation in iron oxides or precipitation in zinc minerals might be an issue, and it's more likely at higher zinc concentrations, and the precipitate's not extractable by DTPA. One way we can kind of get a handle on this is actually look at the correlation between total zinc and iron. For the iron oxide story, and it does seem like total zinc is very highly correlated with iron, suggesting that iron in some way is maybe controlling zinc concentration. One of the most likely explanations for that is in iron oxide precipitates. So zinc gets included in them as an impurity, which would tend to, in some ways, agree with that particular result. Okay, so, and as I said, if you're fussy, we can look at significance of correlations and things. So these are pairwise two-sided p-values, unadjusted, so anything less than 0.05. The one that we just looked at, correlation between total iron and total zinc, highly significant. So in other words, the probability of seeing the results that we have, if the null hypothesis is true, the null hypothesis meaning no relationship, is very, very small. So we can reject the null hypothesis and assume by that logic that there is a real relationship between total zinc and total iron in this case. Okay, adjusted p-value is really correct for the increased likelihood of getting a false positive with multiple comparisons, so that p-values become a little higher. Now, whether you trust Holmes' correction or not is a moot point, I guess. Okay, so that's correlation, and another simple way we could look at the data is to have a look at, say, differences in extractability of zinc for high pH, low pH, high iron, low iron. So in that case, we need to create a factor out of a variable. Okay, so just quickly, how would we do this? Well, first of all, we'd have a look at the distribution of a particular variable of interest. So let's scroll down, have a look at total iron. Let's make sure we have lots of bars on our histogram, basically, and we don't really need to plot by groups. In fact, we can't because we don't have any. So okay on that, and there's our histogram there. Now, what we can see from that is it's by no means clear that we have a bimodal or multimodal distribution. So, but as mentioned, we can be and somewhat arbitrary about it, and we can say that high iron, remember this is log iron concentration, so we have an iron concentration of 10 to 4, or 10,000 milligrams per kilogram. In other words, 1% is our threshold. Below that's low iron, above that's high iron. Alright, so how do we make an iron category out of that? Well, the way to do that is data, manage variables, and recode variables. So we're going to make the new variable a factor. So we're going to pick one to recode, and of course that would be, it doesn't really matter, let's make it iron total, and we're going to call it iron range or something like that, and we'll say that between a very small number, let's call it, and colon in between the lower and upper ends of the range. Okay, 1E4 or 10,000. We're going to say that is iron less than 10,000. Alright, so we need to make another entry in here. So, and from 10,000 to a million, we can't exceed that, obviously. You can't have more than 1 million parts per million. We'll make that iron greater than 10,000. If just in the instance that there are missing data in there, it's always good to put an error catcher, if you like. So if it doesn't fit into either of those categories, we'll make it not available. But I don't think there are any missing data, but let's do that anyway. Okay, so now you can see that in our messages we've created another column, and what we should do then is generate some statistics. Actually, it's probably easy to, we're going to make, so our data set's called E5, $symbol, FE.range, that's what we called it before. Click submit on that, and we can see that in our iron greater than 10,000 ppm, we've got 12 observations and 14 lower. There's a little bit of a problem because the order has become alphabetical, but actually intuitively I would expect for graphing and things to have less than first. So what I'm going to do is quickly change that and reorder my factor levels. So that factor there is the only one we have. We'll keep the same name. Do I want to overwrite it? Yes. And we'll make the greater than one second and the less than one first. Click OK. Alright, so if we run that previous line of script again, we can see that we've got them in the right order now. So if we, for instance, made a box plot of our variable of interest, plot by, alright, so we can plot by range, options, don't need to change any of that. Okay, there's our box plot, right? And if you want to put some estimate of variability or confidence interval around that, we can, as some of you know, make an edit to our script and submit that, and we get an estimate of, so it looks like just on that simple graphical analysis that, and remember for box plots, this is the confidence interval around the median, so it's not quite as satisfying. So for iron less than 10,000, we've got slightly higher extractability than we do if iron is greater than 10,000. Okay, so low iron, high, high iron, low. Is it a real effect? Well, how do we assess that? The way to do that is to do a mean comparison. So there are a couple of ways we can do that. It's either an independent samples t-test. So with the only possible groups, iron range, and our variable of interest, and options, just make sure that we've got a two-sided test and we're not assuming equal variances, right, within each group of iron concentrations. And click OK, and we get some output. So it's telling us that we're doing the Welch two-sample t-test, which doesn't assume equal variances in each group, and our groups are iron less than 10,000 and iron greater than 10,000. It's saying that the probability of seeing the difference that we do if the null hypothesis is true is quite low, so we can reject the null hypothesis, and that's supported by the confidence interval for the difference between the means, not including 0. And here are the values of log transformed zinc DTPA over zinc total for each group, which hopefully roughly match what we saw in the box plot. Okay, so about 0.5-ish. So the actual mean is probably below the median, and 0.75-ish, which looks like the median's roughly equal to the mean. Alright, so if you don't like t-tests, you could do the same thing another way. Statistics means one-way analysis of variance. We can only use that group again. There's no need to tick pairwise comparisons of means because there is only one pair. And we hit that again, we're getting similar results, right? So our null hypothesis can be rejected because of the p-value there, and it's although it doesn't output a confidence interval for difference, we've got our two mean values for each group, right? So maybe that's useful. Final thing that we thought about doing, of course, was to look at a regression model. Okay, now let's do it simply first, and again it's easy to do in R Commander. Statistics, fit models, linear regression, and our response variable is our variable of interest, zinc DTPA divided by zinc total, and our explanatory variable could be, let's do it simply at first, make it just iron concentration. Alright, and that's about all we need to do. Okay, so we've got a regression model here. Now, it's kind of, we can only just reject the null hypothesis by conventional null hypothesis testing. Well, in fact we can't reject it, but only just. But we do see that we can explain about a third of the variability in zinc extraction by DTPA with just iron concentration, and it's probably a good idea to check this sort of thing with a graph, so we'll do that. Our x variable, of course, being iron concentration, and our y variable being our fraction of zinc extracted by DTPA. Okay, turn off the chart junk. Let's make things a little easier to see by making those sizes a bit bigger, and maybe even, okay, I know what the plot characters are, so I can do that with impunity. Okay, so we get a graph that looks like that, so the negative relationship that we thought we had. Now, because of the scatter, the significance is not high, particularly given the relatively low number of points. We only have 26 points, and the process will also identify influential points on regression, so 0.26 and 0.7 if we want to chase up what they are. So as far as the regression is concerned, I guess we could interpret those as potential outliers. Alright, so we have that, but we kind of deduced that already from our correlation matrix. How can we make a more interesting regression model? Okay, so let's get rid of that for now, and we can go back to statistics and linear regression. We can actually add some more explanatory variables into our model. So again, I'll do this fairly simplistically, just choose a few. If we hold down the control key, we can add them to the ones that we already have. So let's add some major elements into the mix. Let's add EC. We already have iron in there. For argument's sake, let's add potassium, sodium, organic carbon, phosphorus, what the heck, and total zinc. Right, we'll leave that there for now. So it's going to create a different regression model, and we'll apply that. Okay, now let's have a look at the output here, because we get a whole lot of output. And here's our table of coefficients, basically, and with some measure of statistical significance attached to all of them. Right? And we also get some sort of summary of the regression model. So it just about doubled the amount of variability in our dependent variable. That's the fraction of zinc extractable by DTPA. And we still have a significant relationship, but it certainly seems as though not all of the predictors are very good. Now, we don't, as in Excel, we don't have to weed them out manually one by one. We've got a tool in R command, which is just implementing some of the stuff in R, where we can do stepwise model selection automatically. Alright, so usually I just accept the defaults. The criterion basically is an information criterion, either Bayesian or Akaki. They're similar, and different ways of deleting and reintroducing our predictive variables. Okay, so click OK on that. What's that, sorry? Okay. And we've come up with a new set of parameters after going through a number of steps, missing out and adding in. And you can see that we're getting a different value of our information criterion, and we want to try and maximize that at each step. Right. So we end up with our final model, and here's our maximum value of information criterion and a final model. So what I would then do is to adjust our model to only include those parameters. So what I can do is copy that bit of script up there, go down to the bottom and paste it in. Let's make a different regression model, 3A, and we only have in that calcium, iron, organic carbon, and total zinc. Alright, so we run that, and lo and behold, all of our predictors come out as significant. Still got pretty good R-squared, in fact it's a bit better in this case, and so we've got a pretty good model. And one way we can, if we select that model we just created, have a look at the effect of each parameter is to go to our effect plots. Select all the predictors, click OK, and there we have quite a handy sum model. Is telling us that there's a negative effect of total calcium, total iron, and total zinc on the proportion of zinc extractable by DTPA, and organic carbon has the opposite effect. Okay, so we can think about why that might be, and that would form part of the report on this.